Last time we started introducing all the concepts concerning WebGL. WebGL as a part of the OpenGL implementation, etc. Today we are going to improve our understanding of the, let's say, 7-8 steps that you need in order to draw something on the canvas. So I'm explicitly referring to the last part of the lesson, this one. All those steps. The first one, in which we define an array of vertices, elements, we are going to use for drawing. A second one, in which we allocate, reserve some memory on the graphic adapter to store those values. The binding, meaning that since we are using a state machine, we explicitly state that we want to use that buffer, that portion of memory with those data, and a formatting of this blob of data we send into the memory. For today too, we are going to skip the part concerning explicitly GLSL. We are going to use some pre-generated shaders. Starting from next lesson, we will address the topic of shaders, which is also the topic you require to know at your exam, so pretty much important, but without this introductory part can be hard to understand completely. And once we have on the memory of the graphic adapter both the data that we want to draw, both the program that explicitly specify how we want to use those data, then we just have to put those two parts into communication by retrieving the input addresses the program is expecting to find the data we want to draw, enable the communication, and then, after all, draw everything. There are 8 steps, more or less, that we already saw last lesson. It may, as I told you, it may seem complicated, but the good news is that the same 8 steps are required for each kind of object that you want to draw, from the simplest one to the most complicated one. So, if we go into the utils folder that I zipped and uploaded on the BIP website, we can start copying those two files that more or less are the same that we used last lesson. So we copied them in a folder that we want to use for coding, and then we can open them. Okay. This is the drawing part and the HTML part. Okay, make it a little bit bigger. So the first thing that we want to do is going from a very simple geometric triangles to a collection of triangles assembled in the form of a cube. So another file that you want to copy inside the same folder you are working in is the first cube definition.js. Okay. As you can see, in this file, which have an extension .js, you see, I have tabbed in lines of 3 columns just to say that each row is contains the x, y, z coordinate of a given vertex. But of course, from programming point of view, this is just an array, just a very long row of a number of values. Okay, so we are going to use this one. The effect that we want to have, to obtain is this one. Okay. Is this? This is the cube that is coded. So, of course, in this picture, you just see 7 out of the 8 vertices that the geometry of a cube has. But for us, the geometry vertices and the vertices that we are coding are not the same thing. That's why in many graphical programs, vertices are not called like that, they are more control point, because associated to that position in the space, we can have many more information than just the x, the y, and the z position. So for now, let's call them vertices. Proceeding on, you will see why it's a little bit not precise, it's not that precise as a definition. So this is the cube, it is centered at the origin of the axis, and each of its dimensions are less than 1. So we already have normalized values for this cube, all in the range -0, -1, 1. So back to the code. The first thing that we need to change is row here in the scripting. Of course, we are going to load the drawing.js, but we also need to use cube definition. We have to include it basically. Cube definition 1. In drawing.js, you have a stub of the main function we coded last time. In the same way, briefly, the canvas is going to be the portion of the space reserved for drawing. In the canvas, we want to create a context, which is the state machine holding all the information for WebGL, all the logic of the WebGL interface. We get a context out of the canvas, usually called WebGL, but for backward compatibility, some browsers still call it experimental WebGL, so we put as an alternative one or the other. If we are able to get a context, then GL is going to be true, and we can put the logic of our code here. Otherwise, an alert will say that it's not possible on that browser to proceed more. So, the first thing that we need, another thing, last time we just coded up to a 2D image. Now we want to go to the 3D. So we need to add all the matrices that allows us to make a projection in the space of some geometrical, some geometry, some topology of some object. So in order to have all the proper data when we need them, the first thing that we need to code are a couple of variables, W and H, and we store in that variables the client width, basically how big is our context, and the height. Okay, later on we will see why we need them. Then we start with the usual procedure. So the first thing is to create a buffer object for the vertices, and we do using create buffer. So we allocate the portion of memory that we need. Then we bind it to say that is the one we want to use now. Bind buffer. We specify that the buffer is going to be an array buffer. Sorry, all uppercase. And it is stored, its handle is stored inside this variable here. You see the procedure is exactly the same of last time, because it doesn't matter the data that you provide, the steps are the same. And then we specify with buffer data, we send the data inside the buffer. The only thing we need to, to do, since with JavaScript we don't have a strict type for the variables, but WebGL does require that the variables are typed, we need to transform this array vertices in an array of floating point number. Okay, in this way we make the conversion on fly, and then we specify that we need the buffer just for a static drawing, meaning that the content of the buffer is not changing during the lifetime of the application. Okay. Another thing that may be useful, maybe not now, but as we make the program more complicated, are two more lines that are clear color. I will explain later why, just not forgot to put it here. With this, I'm specified that I want a canvas background which is black and without alpha. It's just an RGBA code. And then I want to put my viewport, which is the area of the canvas that I want to visualize, starting from 0 up to width and height. And this is one of the first use of client width and client height. In this way we provide correct screen coordinates. The rest is computed by WebGL alone. So we have to care about the other matrices, the word, the view, and the projection, and create a stack out of that and provide it to WebGL. Okay. At this point we need, you see from now almost anything that we need, we have the data that we want. We create a portion, we allocate a portion of memory on the graphic adapter to store them. We activate the buffer, and then we buffer the data. We send the data to the buffer. The next step is about creating the WebGL shader code. Since we are not coding them, we can go into the snippet and take GLSL1 and simply paste, copy and paste this thing here. Okay. This is a sort of black box for you now, but given some input at the end, we have a shader program, and we want to use that shader program. So GL use program banner program. program because we have a program created here. And program is also a global var. So the handle, yes, the position in memory of our GLSL code is stored in a variable that can be used in many scopes, in all the scopes of our program. Now that we have a program handy to use, we need to declare a new variable which is vertex position handle. Inside the portion of memory in which our program code is stored, there is a position called pos1, at which position we need to send the data that are inside the buffer. So we are explicitly collecting that position. gl.enable Now we are allowed communication between the program and the buffer with the data. And then we format everything that we send with the GL vertex attribute pointer function, always vertex position handle. We say that each three values, we have three values defining a vertex. We can have more and we will see them. They are going to be all floating point values. They don't need normalization, so it's false. And for now, we don't have any other information to pass, so this is 0, and also the other one is 1. At this point, we can try to get a GL draw array, which is the actual draw call, draw arrays with an S. GL lines, starting from 0 up to 24 values. 24 because we have 24 rows for defining our cube. Why we need 24? The first thing that we are trying to do with this cube is just to draw its wireframe, meaning that we want to draw only the edges of the cube. The cube will be empty and we only want to draw its edges. So that's why we need 24 values, because we need to replicate the value of a vertex for each of the edges that are defined by it. So if, for example, we look at this vertex here, you see that there are three edges that use that vertex. So we have to specify again the value of that vertex thrice. Of course, this is not a good practice. It's not good for performance because we just have redundancy in data. There are different strategies depending on the situation that allow you to avoid specifying more than once the vertex. Okay, so if we now try to execute our code, aside from the many errors that I expect, Okay. Control Shift I, and you open this window here, which is pretty useful for the console. Okay, now the cube has been drawn, but it seems more like a rectangle. Well, that's because we don't have any matrix for projection yet. So, because we are not projecting any of its vertices inside a 3D world, the 3D world has not been created yet. You just see the vertices overlapping one another. Also, is more like a rectangle again and not a cube because of the same problem, because we didn't yet have specified frustum and all things like that. So that's what we are going to do this lesson, specify all the different matrices and see how the different matrices modify the effect, the final effect of your creation. Okay, so for doing this we have to refer to a very basic math library. This one is something that I coded. It's not that different from the one, for example, in Three.js, which is an open source engine for using WebGL. So aside from the first function, which I will explain later, they are basically for loading JSON formatted models in our application, a thing that is advanced and we will see in a couple of lessons. Aside from this other function which load the shader file, the shader code from an external file instead of hardcoding in our main application, there is a math library with a couple of basic functions like the transformation from degree to radius, the creation of an identity matrix, function for inverting a matrix, for transposing it, multiplying them together, multiplying a matrix for a vector. Talking when we will see normals, this one will be useful. But for now, we will see the function that allows us to create a word matrix for the object, which is a composition of the translation, rotation, x, y, and z, different rotation for each of the axes, and a scale. This is a proportional scaling matrix creation. We don't scale anything unproportionally. But and those functions are used by the make word function. This is for creating instead a new function, and the first one we are going to use is the make perspective. We create the frustum. Okay, we just need a couple of, this is an implementation of the formula that you probably have seen in the theoretical part, so nothing too exoterical, and we put in the right position inside the matrices everything we need. We just need to pass to this matrix a field of view, which is the opening in vertical in degrees, the aspect ratio, because you know that not all pixels are squared, so we want to avoid to have a rectangle, we want a cube, the near plane and the far plane of the frustum. So having this function allows us to create basically the frustum. In order to include the utils in our program, after the cube definition, we of course need to include another script, which is utils. Okay. Back into drawing. At the very beginning, here, global, we need to declare a new variable, which is perspective. You can choose any name you want, of course. The creation of the frustum, differently from the other matrices, is something that usually happens just once in a program. It's pretty rare that you have to change information about the frustum. All other effects, zooming, moving the camera, moving the object, is obtained usually by changing the other matrices. So, because of this, in the main cycle, we just declare perspective matrix as utils make perspective. For example, 90 degrees. As aspect ratio, we can just give W over H. We put the near plane very near, and let's say that 100 is enough as a far plane. And 100 is enough as a far plane for this case, in which we have a very small object which is centered in the origin of the axis. But you will see that when we are going to load more complex models, 100 is not enough. Or you have two options. You can increase the distance of the far plane or scale and reduce the object to make them fit inside the frustum. Okay. And just as a good practice, I suggest you always to log the result of a perspective. For now, this shouldn't be a problem, but proceeding on, if you want to debug your code, it can be helpful to see if there are any not a number values inside the matrix after a multiplication. When you have a stack of matrices, when you multiply many matrices together many times during your cycles, it may happen that you make some coding mistake. So at the end you don't see nothing. Why? Because the matrix have not a number and the shaders cannot use it. But it doesn't alert with any error messages. That's why I suggest you to log by yourself. Since we now have one value more as an input for our shader, we need to change the shader, because up to now the shader program that you just copy and paste was able only to use the vertex data. There is no possibility it doesn't have the possibility to use any matrix. So we delete it, and inside snippet you take GLSL2, which is basically the same code, just have the possibility to have a matrix multiplication. And you can find this multiplication here. You see that we pass a matrix. Next lesson we will see GLSL code in details, in more details. And you see that we multiply the matrix for the value of the vertex, which is a vector 4 made up by the three values that we passed, x, y, z, together with a scale value of 1, because we don't do scaling inside the vertices. Everything else remains more or less the same, but if at this point we passed the vertices to the shader, now we need to pass a matrix too. So we add a new handle, matrix position handle GL get uniform location of matrix. The matrix, how it's called? The matrix. we need to go through the same steps. If before we need to find the handle for the input position for the vertices, now we need to find the input position for the matrix. It requires a different function, but the result is exactly the same. And then after passing, it's better to do that before, but it doesn't change really. GL dot uniform matrix for floating values. We send it to this position, matrix position handle. This is a bug or a feature that has never been changed in WebGL implementation. When you pass a matrix to the shader, I don't know why the second parameter should be always false. If you look at the documentation, they say that at this position the false or true parameter stands for do you want to transpose or not the matrix? With false, you say no, I don't want to transpose the matrix. Use it as I pass it. But if you put it to true, nothing happens and the program crashes. They never change it. Probably they keep the feature for future implementation, but for now you just have to put a false in there, and then if you want, as in our case, to transpose the matrix, you have to use your own function. Transpose matrix. We need to transpose it. This is also a backward problem. We organize all the matrix multiplication in one order, and you know that if you change the order from left to right instead to from right to left, the results is not the same, and you don't get the results you want. That's another oddity, because the first code that we made was for OpenGL. OpenGL multiplies matrix in one order. WebGL, by default, multiplies it in the other order. So in order to have, we never change it. Probably next year I have to recode this part. But for now, just add a util transpose matrix, which indeed solve only this bug, and put here perspective matrix. So now we are passing also this matrix. Since we are passing the values directly from the client application to the shader, no enabling is required, which is instead required when you make two portions of memory communicating one to the other. In this case, so we just need to send this uniform matrix. So everything is more or less the same. There is a problem. Oh yes, I forgot to copy inside the folder the utils file, a step I forgot. And of course, the code was complaining that it wasn't able to find. Okay, so again, we have something. I don't know if you see, there is a cube somewhere, but again, we don't see the 3D. So let's try to see why. For example, let's change from 90 degrees to 150. In make perspective, let's change the frustum. Now we start to see something 3D-like. The problem is that we don't have a camera. So by default, since we didn't specify nothing about the camera, our viewpoint over the 3D world, we are standing at the center of the axis. And since the cube is also at the center of the axis, we are looking at the cube from its center point. The next step, is to create a different viewpoint in order to see better what's happening. Okay, and this is easier than before. We just need to add another matrix, which is the view matrix. So we switch back again here, and we add a view matrix. So we have a perspective and a view, but since we don't want to pass too many matrices, we just want to pass the stack of the matrices, the word, the view, the projection, multiply together and then send. We need the stack matrix, let's call it that way, the multiplicated matrix. So let's call it projection. Okay, and we have the three matrices that we need. So just to remember, this is the stack matrix. This is the perspective, of course. And this is the camera or view. Okay. Let's switch back to 90. And let's create the view matrix. So simply copy view matrix is equal to UTS dot make view. If I recall correctly, make view. So make view instead requires a center for the camera expressed along the XYZ coordinates, an elevation and an angle, so the rotation and the two axis rotation. Of course, there can be also this the rotation along a third axis, but it was not important, so we don't implement it basically. So we use this make view and we create the camera. Let's say that we want to put the camera in 0.5 example and 1.0. So it should be closer to the origin of the frustum in this way, and just a little bit rotated minus 30 degrees toward left. And then the projection matrix. Projection matrix is going to be just a multiplication of those two matrices. So it's utils dot multiply and we put the perspective matrix and the view matrix together. So we have the projection matrix that should allow us to better experience 3D. And we also need to change which matrix we are sending. So in the lines GL uniform matrix for FV, we need to switch to another matrix. And now we have the cube. Finally, we have the cube in wireframe, of course, but the cube is there. Okay. If you have any questions, please ask. Otherwise, we can take 5 minutes break. So I check the recording, and then we see everything about how to move the cube around, to move the camera around in the scene, and finally how to fill the cube, not having only the edges but all its surface. Okay, take a break.